Hello, this is the next video in my series of videos on the discriminant. This example here is a classic kind of exam question. Find the values of p for which the equation px squared plus 2 outside of p plus 2 x plus p plus 7 equals 0 has no real solution. It's from exercise 3I and it's question 7 if you want to check it later. Let's break this down a bit. Find the values of p. So we're trying to find a specific value or values for p for which this equation is true. P you can think of as being a specific number. It's standing in for something that we don't know, but it's a specific number, as opposed to x, which is a variable of a function. The function depends on the variable x. So we see P in a slightly different light, for which the equation, there it is there, quite long, and we'll break that down in a second, has no real solution. So as soon as you see this kind of context, you should think discriminant, because I have a test for no real solution. If I just zoom out and go back here, remember that there are no real solutions, no real roots, no x-intercepts when the discriminant is less than 0. So that is your buy-in, I suppose. Let's write down what A, B, and C is, and I'll just take this slowly so that you can get a sense for it. Remember that A is the coefficient of the x squared term. Now, I know p is a variable and not a number, but it's kind of like it. It kind of acts like the coefficient of x squared. So effectively, A is equal to p. B is the coefficient of x. Now, this whole big thing here is really just a number that we haven't yet worked out the specifics of. So everything bar the x is effectively the value of b. So b is equal to 2p plus 2. C is equal to the constant value, the value that is not attached to the variable x. It's not just p and it's not just 7, it's both. Added to the x squared and the x term is this expression here, p plus 7. It's an expression rather than a single number. So C is p plus 7. And they are our three numbers that we need to put into the discriminant. Okay, let me start the work here. I've got another box that I can write in, but I'd rather leave that for other things. So let's just continue on here first. So the discriminant is equal to b squared. So I've got 2 outside of p plus 2, all squared, minus 4. And then I've got a, which is p, and c, which is p plus 7. I used square brackets because I knew that I was starting to use round brackets as well. I tend to change the shape of the brackets when I've got multiples of them, just to make it nice and clear. Now, this left-hand side here, I have something multiplied by something else squared. And our index laws say that if I have two things multiplied together and squared, each thing gets squared. So that's going to be 4 outside of p plus 2 all squared. And I'll just get rid of some of these unnecessary brackets here now. 4p outside of p plus 7. I'll now start expanding, and I'll have 4 outside of p squared plus 4p plus 4. That's recognizing that it's a perfect square and using the pattern. Square the first, square the last, and twice the product in the middle. And I'll also expand this bit here, minus 4p squared minus 28p. Okay, that's equal to 4p squared plus 16p plus 16 minus 4p squared minus 28p. And that's equal to, well, the 4p squareds will cancel out. I'm just going to put little ticks so I remember what I'm doing. So the 4p's have cancelled out. 16p minus 28p is negative 12p. And then I've just got my 16 left over as well. Plus 16. Okay. And that's the discriminant. The discriminant is minus 12p plus 16. Now, the fact we haven't used yet is that for no real roots, no real solutions, no real x-intercepts, the discriminant is less than 0, i.e., I'll just zoom out so you can see both at once, otherwise it's a bit tricky to see, i.e., minus 12p plus 16 has to be less than 0. Now, when you're working with inequalities, that means less than or greater than, then it's really important that you don't make assumptions about what you can and can't do. So, for example, if it was an equation, I could just subtract 16 from both sides and divide by negative 12 and I'd be done. But when it comes to drawing an equation, solving an equation, I find drawing a graph can be quite helpful. So if I draw the graph, and note my axes now, this is not an XY graph, but this is going to be a P versus delta graph. Then this is going to be a straight line graph with a x-intercept, or a p-intercept really, like so. If I set minus 12p plus 16 equal to 0, then I'll have 12p equal to 16 by adding 12p to both sides. And then I'll divide both sides by 12 to get 16 over 12, which is equal to, let me see now, 6, 4. So I'll have 4 over 3, 1 1/3. Okay, so I'm going to have 4/3 and 0 as my x-intercept, and I can see that I've got a negative gradient, and so I'm going to draw my line. I don't care what the y-intercept, believe it or not. I'm just going to draw my line like this. Now here's the trick. Once you've drawn your graph, which doesn't take very long to do, can you see that if delta is going to be less than 0, then it's going to be all of these solutions here below the x-axis, because below the x-axis is where delta is less than 0. At this point, delta equals 0, and all of these solutions here has delta greater than 0. So for no real roots, I need to say that P can be anything along here. So I can conclude in the right color, therefore, for no real roots, P is greater than 4/3. See? So by drawing the graph, you can't go too wrong. If I was asked where would it have one real root, I'd say P is equal to 4/3. And if I said where does it have two real roots, I'd say P is less than 4/3, because that's when delta is greater than 0. So I'll leave it there. There's more complicated problems that involve, you get an expression here that's a quadratic instead of a linear one, and that's its own trickiness, but I'll put that in a separate video so this one isn't too long.